I am audible to everyone. Okay. So in earlier classes, we learned about this iterative methods and how to find their approximate use of iterative methods to find the approximation root of nonlinear equations like algebraic and transcendental equations. So today we find what is the error between the exact root and the approximated root that we obtain through any iterative method. So in the first we define what is the rate of convergence. So an iterative method is said to be of order p, or we say that it has a rate of convergence p if p is the largest positive number such that there exists a constant c which is not equal to 0, like this: epsilon k plus 1 is less than c into epsilon k raised to power p. So what is this epsilon? So here xk is the approximated root obtained at kth step, and this xi is actually the exact root of the problem. So xk is the approximated root we obtained through any iterative method, and xi is the exact root, and the difference is the error. So this is the error between the exact root and the approximated root, and we're representing this error by epsilon k. So epsilon k is the error at the kth step, or kth iteration, and epsilon k plus 1 is the error at the k plus 1th iteration. So if we are able to find such an inequality, like absolute of error at k plus 1th step is less than or equal to a constant c into error at iteration k raised to power p, then we say that the method or the iterative procedure have order p. And this p decide the fastness of the method. Like if a method is of order 1, then it is a linear order, then 2, then it's a second order method, or if it is p is like a 10, then it's a 10th order method. So it means that the error the error at k plus 1th step is getting p times better the error at the kth step. Like for suppose if I take p equals to 2, so p equals to 2, and then assuming that my iterative method is of second order method where p is equals to 2, and if the error in the first iteration, like you say epsilon k, epsilon 1. So epsilon 1 is the error at the first iteration, and I suppose its numerical value like epsilon 1 is equals to 10 raised to power minus 2. So I suppose epsilon k is equals to 10 raised to power minus 2. So if I use one more iteration, then the error at the next step, like epsilon 2. Epsilon 2 is actually having error 10 raised to power minus 4. Similarly, epsilon 3 is having 10 raised to power minus 8. So that is 2 is multiplying everywhere. Like and then similarly epsilon 4 is equals to is less than equals to 10 raised to power minus 16. So this is the way the error is, the method is accurating the error. The second order means it raised to power 2 is increasing at each and every next step. So like if epsilon 1 is 10 raised to power minus 2, then epsilon 2 is 10 raised to power minus 4, and epsilon 3 is 10 raised to power minus 8, and epsilon 4 is 10 raised to power minus 16. So if the order of any method is more, it means it's give us better result, in less number of iteration. Now for suppose I am having a method of order 8. If I am having a method of order 8, like p is equals to 8, and my epsilon 1 is error in the first step, epsilon 1 is 10 raised to power minus 2, then epsilon 2 is, the error in the second step is like 10 raised to power minus 16. So if I am having a method with rate of convergence 8, so I am getting the accuracy in the second iteration itself, as compared to that accuracy I will get in fourth step, or after four iteration, if I am having a method of order 2. So if a method is having rate of convergence less, it means it's a slow method, and if a method having a rate of convergence more, then it is a fast method as compared to the previous one. So like this is the significance of this rate of convergence. So we already learned the method, Newton-Raphson method, and this secant method. So we'll find their order of the error or their rate of the convergence. So we'll start with the rate of convergence of Newton method. So for this, first we have to remember what is the formula for the Newton-Raphson method. And we know that the formula for Newton-Raphson method is xk plus 1 equals to xk minus f dash of xk divided by, oh sorry, f of xk divided by f dash of xk. Wait a minute. This epsilon k plus 1 epsilon equals to epsilon k plus epsilon minus f dash of epsilon k plus epsilon upon f dash k epsilon k plus 1 epsilon. So to get this, we start with this secant method, so that we write our basic assumption. So we will start with this secant method itself. So here in this secant method, this is the procedure. If you remember, xk plus 1 equals to xk minus xk minus xk minus 1 upon f of xk minus f of xk minus 1 into f of xk. So here we have already assumed in this previous when we are defining the definition of a rate of convergence, in defining the definition of the rate of convergence. So here, like we have already defined, this is the error epsilon k is equals to xk minus epsilon. So this is the error at kth step, and epsilon k plus 1 is the error at the k plus 1th step. So here epsilon k plus 1 k is the error at k at the step, and k plus epsilon k plus 1 is the error at the k plus 1 at the step. So we can rewrite this expression epsilon k plus 1 equals to xk minus epsilon as this xk plus 1 equals to epsilon k plus the exact root xi. Similarly, we can do with the xk also. So now these xk and this xk plus 1 we will substitute in this method. So once we substitute this in the method, we will have this one, because here we have xk plus 1 in the left, and here xk plus 1 is like this one. So we substituted here epsilon k plus 1 plus xi, and xk is epsilon k plus xi, so we have substituted here in place of xk. Similarly here in place of xk, in place of xk minus 1. So since xk is like this epsilon k plus xi, similarly xk minus 1 is epsilon k minus 1 plus xi. So this is written here, and then like this. So wherever xk minus 1 and xk plus 1 is there, we rewrite them in terms of error plus the exact root. So the and we have substituted all these value in the given method itself. Sim- and then we can see that this xi can be cancelled out here, this xi can be cancelled out here, and here also. So after cancellation, we can see that in numerator we have here epsilon k minus epsilon k plus 1 here, and f of epsilon k plus 1 plus xi divided by this. And then we know the Taylor series expansion of the function this epsilon k plus xi. Here this we are expanding this f of epsilon k plus xi in powers of epsilon k and about the point xi. So we expand this, we will get this one f xi plus epsilon k f dash xi epsilon k square f double dash xi upon 2 factorial, like this till infinity. Similarly, in the denominator, we also do the same thing. F of epsilon k plus xi minus f of epsilon k minus 1 plus xi, and we expand both with the help of Taylor series expansion about the point xi. So the expansion of this about the point xi, we have this one, and similarly we have this one. Now we can see that this f xi will cancel out by this f xi, and this f dash j will take common outside from these two terms, and we have this epsilon k minus 1. Similarly, we can take f double dash j upon 2 factorial common from these two, and we have epsilon k square minus epsilon k minus 1 whole square by 2. So like this we will get, since we are assuming here j is the root of the function fx, so it means f of j is 0. So we'll substitute here f of j is 0. We have substitute here also 0 and 0, even though they are cancel out, but if we substitute there also, so this f of j will be 0 everywhere, as this j is the root of the given equation fx. So after taking this f dash j common, we have in the denominator like this, epsilon k minus 1 into f dash j. Similarly here, epsilon k square minus epsilon k minus 1 whole square f double dash j upon 2 factorial, plus like this we will get till infinity. Similarly in the numerator we have the same thing, this thing is cancelled out already, as this one is 0. So we have here. Now again, we know that in each and every step here we are having a term like epsilon k minus epsilon. Like if we think about the third term is like here epsilon k cube minus epsilon k minus 1 cube f triple dash j upon 3 factorial. So we have taken this epsilon k minus epsilon k minus 1 factorial factor common from all these terms and cancel out. So we have first taken this factor from all this term in the denominator outside of this expression, and then this factor will cancel out by the numerator factor, and then we will have this epsilon k f dash of j plus epsilon k square f double dash j upon 2 factorial till infinity, and then f dash j plus epsilon k minus 1 f double dash j upon 2 factorial, because here we are having this epsilon k square minus epsilon k minus 1 square. So if we factor it, we will get epsilon k minus 1 into epsilon k plus epsilon k minus 1. So this epsilon k plus epsilon k minus 1 will remain in this in the multiplication of this f double dash j upon 2 factorial. Now the next step is to take this common f double dash j from the numerator and denominator. So if we take f double dash j and f dash j in the numerator and denominator, because there is no f dash j present in this term, so this f dash j will go in the denominator, and like all the terms present here. Similarly here also. And then this f dash j is also cancelled out, and then we take this denominator term in the numerator by taking its minus 1 power, and then we assume this whole thing as like a capital X, and then we expand it like 1 plus x raised to power minus 1. So like this we expand. So if we expand this like this one, this, so we have this 1 minus epsilon k plus epsilon k minus 1 f double dash j upon 2 factorial f dash j till dot dot single power, then second power, and then third power. Like this we will get these expressions. And now we start multiplying like terms here. So we now multiply this epsilon k to this 1. So if we multiply this epsilon k to this 1, we will get epsilon k, and the 1 minus is already outside. Now we multiply this epsilon k square upon 2 factorial f double dash j upon f dash j to this 1. So we will get the second term, and the third term and other terms we will get, we represented by this three dot dots. Plus we multiply this epsilon k to now this term. So if we multiply this epsilon k to this term, epsilon k plus epsilon k minus 1 like this, we will have this term. So the term next to it is having epsilon k, or multiplication of epsilon k minus 1, epsilon k square, 3 degree terms in epsilon k and epsilon k minus 1. Similarly, here also we have like epsilon k cube upon 3 factorial f triple dash I upon uh, f dash I. So like this, so we neglect those terms. So finally, and this will cancel out also, epsilon k minus epsilon k minus this. So we have this one, epsilon k, because this is having second degree term in epsilon k, and this is also actually like a second degree terms in epsilon k's. So we'll consider this because next terms are having third degree and higher degree term in epsilon k, or in terms of product of epsilon k into k minus 1. So we are assuming their contribution is negligible in terms of the contribution of these terms. So the contribution of the third degree terms we are assuming negligible in terms of the second degree terms. So this two term will play main role in the deciding the error. So we'll consider these two, and other terms we are neglecting, or we say that these are these kind of terms having higher order degree, like you can see here, epsilon k square and epsilon k minus 1. So it's like a third degree term. Similarly, epsilon k into epsilon k minus 1, which is also like third degree terms in terms of error, because this is 1 power here and 2 power here. So we have representing the other terms are order of this term. And now we multiply this. So we can see here also, like here we are having epsilon k square. So epsilon k square multiplied to this, we will get another epsilon k square upon 2 factorial, like the same term. So this term is also cancelled out. So this term is also cancelled out. Only this second degree terms in terms of error will remain, and other terms are having higher and third and higher order terms in terms of product of error. And so we are assuming the contribution of this error is more as compared to this. So we are neglecting this thing. So now we have, or we are able to write epsilon error at k plus 1th iteration is equals to this 1 by 2 f double dash I upon f dash I epsilon k minus 1 plus this term. But this is not the form of the error equation. Like when in y ask what is the error equation, so you have to remember what is the form of the error equation. So error equation form is this one. We are always expecting this kind of equation. Absolute of epsilon k plus 1 is less than equal to c into epsilon k raised to power p. But the term here we are getting in the secant method, it is not of this form. So we have to somehow to convert the expression in this form, like epsilon at k plus error at k plus 1 is less than equal to some constant into error at kth step. So how we do that? So we know that the our error equation is always of this form, like epsilon k plus 1 into some constant, and this constant like will decide less than equal to or equality, and except epsilon k raised to power p. So by default, like we assume that this secant method is of order p, and later we obtained what is the value of p. So the from the method we are already obtained equation number 11 as the error equation, but it is not in the form that we have decided, so that we can decide what is the error order of this method. So to convert this equation 11 to in this form, we are assuming that the method is of order p, and if the method is of order p, then its error equation is in this form: epsilon k plus 1 is equals to a epsilon k raised to power p. And similarly, this k can be replaced by k minus 1, you will get this one. from the above equation. And here you can write like this, you multiply this, so you divide by this a both side, you will get epsilon k upon a is equals to epsilon k raised to power p, and then you take pth root both side, you will get this from the above selected area. So you will get this, so epsilon k minus 1 you are getting this one. So now what you do in equation number 11, in this part only, because this is the deciding factor, so in this part only we uh, keep this epsilon k as it is, because we want epsilon k is equal to some constant into epsilon k raised to power p, and this epsilon k minus 1 we replaced by this one, a raised to power 1 upon minus 1 upon p, and epsilon k raised to power p. So after substituting, we will get this one. And here we can simplify epsilon k raised to power 1 plus p, a raised to power 1 a minus p. And this epsilon k, and how we divide this epsilon, because we have to obtain this value. So this epsilon k plus 1 is also replaced by this a raised to power epsilon k raised to power p. So we have this one. And then finally we have this one. We take this. So here, since this is epsilon k terms are here, so this p should be equals to this 1 1 plus 1 upon p. So comparing both side powers of epsilon k, we will get this p equals to 1 plus 1 upon p, and then we have this equation, and then we know the formula to solve the quadratic equation like this, like like this form, like this we can get p equals to this one from this equation, and we take this plus sign, and we will get this. So the order of the secant method is this one, 1.618. So this is the called the order of error of the secant method. So here we have obtained the value of p. So we can write epsilon k plus 1 is equals to a into epsilon k raised to power 1 plus 1.6 something. So this is the error equation we got from the this secant method. Now you remember this concept here again. Epsilon k is equals to the error at kth iteration is epsilon k minus epsilon, and epsilon k plus 1 is equals to this one, epsilon k minus epsilon, and we can write xk like this and this. So it means we can replace wherever xk is there epsilon k plus xi, and wherever xk plus 1 is epsilon k plus xi. So we use this to find the error equation in the Newton's method. So what is Newton method? If you remember, this is the formula for Newton method, this one. Xk plus 1 equals to xk minus f of xk divided by f dash of xk. So this is the formula for Newton method. So in the formula of Newton method, because we want to find its error equation, so wherever xk is there, we replace this xk plus 1 by epsilon k plus 1 plus xi. Similarly, this small xk is replaced by epsilon k plus xi. Here in the f image is also. So in this formula of Newton method, we replace xk and xk plus 1 by their error plus root, and we will get this equation. So we have substituted in the Newton-Raphson method. This is like xk plus 1. This is like xk minus f of xk divided by f dash of xk. So we have replaced xk by epsilon k plus xi, and f dash and xk plus 1 by epsilon k plus 1 plus xi everywhere in the Newton step. So this is Newton step where we have replaced the xk and xk plus 1 by xk plus epsilon k plus 1 xi plus epsilon this. So we have replaced the xk by the error plus roots. And now the next step is easy. This xi is cancelled out, and the numerator and denominator we expanded through Taylor's expansion. In the numerator, we are expanding the function f. We are expanding the function f about the point xi. So we have expanded the numerator f of epsilon k plus xi with respect to xi, but in the denominator we are expanding the function f dash. So you have to remember this thing. Now in the denominator we are expanding the function f dash xi, the function f dash about the point xi. So if we do, we will get this one. So like in the numerator, the function f is replaced by f dash, because in the denominator we are expanding a new function and the new function name is f dash. So if we are writing it's expanding it about xi, so you will get the first term is because the function name is f dash, so it's f dash of xi, and it's already first derivative is there. So if we differentiate it one more time, we will get f double dash xi upon 1 factorial, f double triple dash xi upon 2 factorial, because in the denominator we are expanding the function f dash about the point xi. So we'll have this numerator and denominator. Since why this is 0 fj, this fj is 0 because xi is the exact root to the function fx. So if xi is the exact root to the function fx, so f of xi is equals to 0, you will get the 0. But in the denominator we have f dash xi, and this should not be 0. So we keep this as this one. Again, the next step is to take this f dash xi common from numerator and denominator, like we already did in the second method. So if we take this f dash xi common from the numerator, and it will be outside, and you can see you will get this kind of term. Similarly, in the denominator, you take this f dash xi common, you will get this one. And whatever is this f dash xi common outside, you cancel out. So the like here little they have already this f dash xi they have taken common from numerator and denominator, and the cancel out also. So we have remaining term in the numerator is this one, and the denominator is this one. Again, the next step is the denominator can be rewritten as this into raised to power minus 1. Again, the same, we will assume that this thing is whole capital X, and we use the expression like 1 plus x raised to power minus 1 is equals to 1 minus capital X plus capital X square, like those kind of terms. So we have expanded it like 1 plus x raised to power minus 1, and this is the expression. 1 minus this plus this expression square, and like this till infinity. Again, the next step is to multiply this to the first term. If we multiply epsilon k to the first term, we will have this one. Now we multiply this to the first term, we have this one. Next, it is a third term in epsilon k, so we will neglect this one because this term will not cancel out. Now we multiply this epsilon k, sorry, this. We have multiplied this epsilon k to this one. We got this epsilon k. Then we multiply this epsilon k to this first term only. We will get epsilon k square f double dash xi upon f dash xi, and 1 minus from this one. Then if I multiply this epsilon k to this, I will get third term degree term, and that I am absorbing in this one. Now we are multiplying this term to this one. So if I multiplying this term to this one, I will get this one. And now if I multiply this term to this term, I will get third and higher order degree term. So I am absorbing all this in this one. And similarly, this is also third degree term, this is also in this one. And since here is a square, so here also we will get the third terms. And so all other infinite terms, we are getting the terms having either epsilon k raised to power 3 or higher degree terms. So we can represent this by order of epsilon k raised to power 3. So we have this one. So we'll take this minus inside, and this will first we will simplify this one. This is like 1, and this is half of this. So this half of this is plus, and this 1 is minus, so we'll get minus half of this. And since this minus goes inside, we will get plus half k square f double dash j upon 2 factorial f dash j. And this can, epsilon k is cancelled out by this epsilon k. So here we have this one, and this is actually coming in the in this Newton method. We are easily coming in the form of the error equation, because here in the left we are having epsilon k plus 1, and in the right we are having some constant. You can say this is c, and I'm assuming this like selected f double dash xi upon 2 factorial upon f dash xi. This I am assuming like a some constant capital C, and then epsilon k raised to power 2. So whatever I'm getting here, epsilon k plus 1 is equal to C constant, where C is this one, into epsilon k raised to power 2. So this is the form of the error equation. And I'm like this term is also there. That's why we have used here approximated terms, or we can have less than equal to also. So because so here we are getting the exact form of the error equation. Epsilon k plus 1 is equals to c into epsilon k raised to power 2. So it means the Newton method is having, because this is p na, and this p is 2 here. So the proof of the error equation of the Newton method is easy as compared to secant method, because in this we are directly getting the error equation, but the secant method we have to do some other kind of calculation. So the order of convergence of the Newton method is 2. So Newton-Raphson method has order of convergence 2, and secant method has order of convergence 1.6. So obviously Newton-Raphson method is fast as compared to secant method. So you go through these proofs of Newton method and the secant method, because last time I asked this kind of like here, you know, the this is the secant method and this is the Newton method, and you know their proof. But in exam I give you a new method that you don't know, and I ask you them find its error, order of error, and you have to follow these procedure to get the error. So practice these two terms, and I will give one question related to this also, so that and you can find the order of the new method. Similarly, in exam also, I will give you some new method, and you have to calculate its order of convergence. So today I stop here. Tomorrow we will discuss this fixed point iteration. This is also very important concept in numerical analysis. And if you have any question, you can ask. Hello.